Okay, guys, well, we're finally ready to put some complex numbers into our matrices and see what the outcome is of all that stuff. So really all I want you to do for today is to watch this video, look at the notes that I'm sharing with you, and then jot down any questions that you have. And then we'll do some practice identifying some of these matrices tomorrow. And if we need to do a Google Meet to answer some questions, we can do that too. So I'm sharing the PDF that I'm going to go through with you as well. So if you want to print that out first or however you do it, you can follow along with the screen and that should work too. So we have here three different classifications of matrices that deal specifically with complex entries. They could work for real matrices too, and there are analogous names to each one of those. But I want to first show you what necessitates the difference between why we would even have to think about complex matrices a little bit different. And it's just a simple matter of our adding and scaling and the implications of dot product. If I give you a complex vector here, v, components 1 and I, and ask you to find the length of it, we know that it's the square root of the dot product of it against itself. So the square root of v transpose v, and it should also not be 0 because it's clearly not a 0 vector, so it has to have some length to it. By the way, this length has to be a real number because it's measuring a distance, right? But you'll notice what happens here when we take v dot v, v transpose v, we get 0, which can't be right because this is clearly a non-zero vector. So that just means that we're thinking about this in the wrong way. V dot v has to be done differently for us when we're dealing with a complex vector because just of the fact that, you need to have a real number as the length, and the real number is going to come from the fact that I squared, what any i's that you have in the vector is -1. And so rather than just v dot v, what we do is this bar over the v, if you remember, means the complex conjugate of v. And we have to do it in this way, where we would take v bar or v conjugate transpose v, because think about what that does is that's going to give us the I squared plus I squared here in this case by changing the sign of it. That's going to guarantee that we're going to have a real number as the answer. And so that's actually taking into account of the fact that, this vector is the way we've been thinking about it, sort of four-dimensional, but we're looking for the length, the total length of all of it. So rather than just plain old v transpose v, it's v bar, v conjugate transpose v to give us the length of this vector as 2, which makes sense if you think about drawing it in 4 dimensions, I guess. But rather than always say v conjugate transpose, the other simpler way to do it is with a capital H up here instead of the capital T for transpose. The capital H means conjugate the first vector and then transpose. And that's for a mathematician named Charles Hermite. And so it is a VH is a Hermitian vector. V Hermitian means V conjugate transpose. So that's a big difference. It's the same thing if it's a real vector. It's just that in a real vector, it is its own, a real number is its own conjugate. But so you can V Hermitian, V works for all cases basically, but it's necessary with a complex vector. Okay, so some implications of that mean that we have to change the definitions a little bit, or the names of what we've been calling some matrices. This says if A is a matrix filled with real numbers, right? We know that when it equals its own transpose, it is a symmetric matrix. And that's because if you think about it, right, you know what a symmetric matrix is. But if it is a complex filled with complex vectors, we have to change that to when A equals A Hermitian. That's because think about when you do like A transpose A, you're really getting, length squared of vectors as the resultant vector. And if you want that to work with a Hermitian, with a complex vector, it has to be A Hermitian A that's going to give you those length squareds as the product on there of all the dot products, basically. And so this is an example of a Hermitian matrix where you notice it doesn't matter really what's on the main diagonal there, except for the fact that it would have to be real, right? And then you just have I, negative I, 3 plus I, 3 minus I, 2 minus I, 2 plus I, and that's going to give you those lengths squared when you take A Hermitian A as a product there. Okay, so are all symmetric matrices Hermitian? Yeah, they are. So that's one thing to think about. So that's a different definition. And so that's the first thing that I'd put at the very top. The next thing was unitary. So if we go through and look at unitary, we know that we've used recently when A transpose equals A inverse. We know that that's the case of an orthonormal matrix because A transpose A equals I when a matrix is orthonormal. In terms of now when it's A Hermitian, we specify that that is a unitary matrix. Are all orthonormal matrices unitary? Yes, they are as well. I guess we separate them because this actually sort of describes here, but the unitary does too, the length of it as well. But orthonormal is very specific, orthogonal and normal. But for that to happen here, the same thing, it would just be that you'd have complex conjugates involved in with all of that as well. And the third thing that I had put up on there was that normal matrices are what we call unitarily diagonalizable matrices. So we've seen orthonormally diagonalizable matrices in the previous chapter. So normal matrices are also orthonormally diagonalizable. And this would be this occurs in this case. Only when A Hermitian A equals A Hermitian would you have the case where you would have same with orthonormally diagonalizable matrix or unitarily diagonalizable matrices as well. Okay. So just to summarize like this one more time, I put that if A Hermitian A equals I, which is A Hermitian, we know that's a unitary matrix. The unit comes from right here, right? Each of those vectors, and the product is length 1 because it's a standard set of basis vectors essentially. And then if A Hermitian A gives you A squared or the length squared of all of those things, it's a Hermitian. A has to be a Hermitian matrix. And I just put here like not everything, not every normal matrix, not every matrix has to be one of those things. Like you could just have a random matrix that looks like that. Okay, so when we have A Hermitian A equaling A Hermitian, a unitary matrix, what I mean by unitarily diagonalizable matrices is that we're able to choose a set of unitary eigenvectors and that you'd have U lambda U Hermitian. So this works again for every real set of matrices we've ever looked at because symmetric matrices in essence are Hermitian as well. And so you've seen these proofs that I have on this page. I'm pretty sure with capital T's here for transposes instead of capital H's there for Hermitian. And what I'm showing you, if you look at this, I'm showing you why if we have A Hermitian, how we can get that to equal A Hermitian A, which is what you have to have, why a normal matrix would be unitarily diagonalizable. So this is a unitary. A is a unitary matrix or a normal matrix in this example here. Okay. So you can look through that and let me know if you have any questions with that. And we have seen this before where you have, let me close on my messages, sorry. you've seen this before where we've seen this proof before as part of spectral theorem, but we saw it with transposes because we weren't even imagining complex vectors at that time. But you can prove that again when A equals A Hermitian, that all of the eigenvalues, even if you're dealing with a set of complex vectors there, that all of the eigenvalues have to be real. And so if you look, we've seen this before with transposes here. If I take this matrix or vector rather, and I don't have a good verb for this, Hermitian it. If I take its conjugate transpose, what comes out of it would be that, in other words, you can prove this because it ends up being its own conjugate, right? So when A equals A Hermitian, this has to be real because I get the same thing back that I put into it. And so that only happens when you have a real number here. So if AV equals lambda V, and I multiply both sides of this by V Hermitian, V Hermitian rather, I get that V Hermitian AV over V Hermitian V equals lambda because this is, we've just shown up here, it's its own conjugate. This is a real number. This is a real number because this is the length squared of V. Right? That's how we find out length in complex vectors. So real divided by real equals real. So all of these lambdas have to be real numbers in that case when A equals A Hermitian. Okay? And then I have here on the last page, we've seen this before with spectral theorem, but we had transposes there. When A equals A Hermitian and AX equals lambda X, all X's can be chosen orthonormally. So what we've done here is defined an arbitrary vector and then the conjugate transpose or the Hermitian version of that. And then just to be clear, this is what I mean. This is a 2 by 2A, I guess, but this is an A, and then this is what I mean. This is the Hermitian version of A there. And we've seen a very similar proof, and I think I used stars at that point in time of how we can show that these two vectors have to be orthonormal. So we have the eigenvalue problem here, ax1 equals lambda x1, multiplying both sides of it by x sub 2 Hermitian. All right, and then down here I have the second eigenvector, ax2. X sub 2 is the second eigenvector. And I am taking the conjugate transpose of both of those, both sides of that equation, and I get an equivalency here. I have in blue, I have A. Now I have, through simplification, A equals A Hermitian in this case, right? But I have A sub 2 Hermitian AX sub 1. I have A 2 Hermitian AX sub 1 equaling this and this in the same case. So if this blue equals each other, then the red have to equal each other. So over here, I'm setting them equal to each other. And once again, we've seen this before, as long as the eigenvalues are distinct, then we know that the dot product has to be 0, and so they're orthogonal. And then you can normalize them. And if there's repeated eigenvalues, we've seen this before, we can still choose an orthonormal basis. So that's like that's the main differences between matrices that contain real vectors and matrices that can contain complex vectors. A lot of it is in the name, but you can name the real ones the same. But this page 1 here is all the whys of how this has to work, so that you get the length squared when you take a vector, the dot product of a vector. It has to be the conjugate transpose of that. Okay, so digest this, look at this, jot down any questions that you have, and I want you to just digest this today. And then tomorrow what we're going to do is we're going to look at seeing if we can identify matrices in any of these categories here. Okay, So think of questions. You can email them to me, or we'll find some time this week to do a Google Meet if that's easier. Probably is. I don't know. So